In this lesson, we're going to develop the ratios of two special right triangles. And you're going to find that in future courses, you're going to be using these two types of triangles over and over and over again. So it's a pretty important thing to get down. The first one we're going to talk about is what's called the 30, 60, 90 right triangle. And we're going to set that one up and talk about some ratios with it. So I have, I'm going to start with an equilateral triangle. And in this equilateral triangle, I'm going to label each side length a length of 2. And then we also know in an equilateral triangle, all the angles are 60 degrees. Well, here's what I'm going to do. I'm going to draw in an altitude. And that altitude creates a right angle. And now we're just going to deal with half of the equilateral triangle. Let's deal with this side over here. So my 60-degree angle stays 60 degrees. Here's the 90 degrees. And the altitude in an equilateral triangle bisects the vertex angle. So instead of 60 now, here's my 30-degree angle. So the next question is, if the full length side is 2, what's going to be the length of this piece right here? If I start as 2, the altitude is actually drawn to the midpoint of this segment, so this length ends up being 1. So here's what we have. We have a right triangle that has a 60-degree angle, a 90-degree angle, and a 30-degree angle. There's 60, there's 30. My full length is 2 because remember that was the original length of the equilateral triangle. Across from the 30 degrees is the length of 1 because the altitude cut that opposite side in half. And now we got to find the other side. If I label him x, we're going to use Pythagorean theorem. So 1 squared plus x squared is equal to 2 squared. 1 plus x squared is equal to 4. That makes x squared equal to 3. And that side is going to be radical 3. So up here I can replace that x with the radical 3. These are the basic side lengths of the 30, 60, 90 right triangle. Alright, so we're going to summarize down here. Again, this is the first of two special triangles you have to remember. If you draw in your 30, 60, 90, remember the 60 degrees is the angle that hasn't been chopped in half. The 30 degrees is the one that was. So if I start with a 2 over here and a 1 down here, the other side is going to be radical 3. 2, 1, radical 3. Now what I can do is all my right angles that are 60, 30, 90 are going to be similar to this one. So what I can do is actually, instead of having a 1, I can make that a 1x, which makes this a 2x, and makes this a radical 3x. So this is a way I can solve a lot of different triangles using these same ratios. The ratio being 1 to 2 to radical 3. All I have to do is, depending on what side I'm given, I can substitute in the value here for x, and I can come up with the different answers. So let's label some of these sides. The 2x is going to be the hypotenuse side. So that's the hypotenuse. And then if you look, we always have a short side and a long side. So the 1x is the smaller side, the smaller leg. And the radical 3x, remember radical 3 is on the outside, is going to be the longer leg. And now we can solve some of these problems. Alright, so let's take a look. Again, we said any triangle with the measures of 30, 60, and 90 of their angles is going to be similar to the triangle I just created. So, if a 30, 60, 90 has a hypotenuse of 16, what are the lengths of the legs? Again, these are going to be similar triangles, so you could draw your 2, 1, radical 3, and there's the 60 degree, and here's the 90, and here's a triangle that's similar to it, 16, and then we're trying to find the other two sides. There's the 60 degree. So the ratios are the same. Again, if you think about it, if this is going to be 2x, and this is 16, basically we're going to solve for x and substitute it in. So if this is 2x, 2x is equal to 16, that means that x value is going to be 8. So if this is 2x and this is 1x and this is radical 3x, that means over here the lengths of the legs are going to be 1x, which is 8, and 8 radical 3. You can check your work by understanding the ratios again. The ratio of the hypotenuse to the shorter side is always going to be 2 to 1, just like over here, 2 to 1. And the ratio of the longer side to the shorter side is going to be radical 3 to 1. So 16 divided by 8, that's the same ratio as 2 to 1. 8 radical 3 divided by 8, that's radical 3 to 1, so it all checks out. Okay, let's try another example. If the short leg has a length of 5, what are the lengths of the other leg and the hypotenuse? So when you have this special triangle, all I need is one dimension and I'll find the others. Again, the ratio between the short leg and the hypotenuse, if you draw out your special triangle, remember this is 2x, 1x, and we'll call this x radical 3, that's the longer side. There's the 60-degree angle. So the ratio between the shorter side and the hypotenuse is 1 to 2. So if this is 5, that means my hypotenuse has to be 10. Again, if this is 5 down here, then this has to be 5 radical 3. So you can think in terms of ratios, you can just think in terms of this special triangle here. 2x, 1x, and x radical 3. The short side is 1x, the hypotenuse is 2x, and the longer side is x radical 3. So now we're going to look at our second special right triangle, and it's called an isosceles right triangle. Well, we know an isosceles triangle has two legs that are the same length, which means our base angles are going to be congruent. So we want to find the measure of those angles. Well, we know this angle is 90 degrees, and we know they all have to add up to 180, and these two are equal to each other. So 90 plus 2x is equal to 180, which means those two are also going to add up to 90, and each one has to be 45 degrees. So this is called a 45 right triangle if it's not called an isosceles right. They both mean the same thing. From here we're going to use Pythagorean theorem to figure out the length of the hypotenuse, c. I have my two sides, so one side length is 1 squared plus 1 squared is equal to c squared. So c squared is equal to 2, which means the hypotenuse in this case is a radical 2. So this is the second special triangle where we're going to memorize the side lengths. So here's our next question. Is it necessary to write all the three ratios? Shorter leg to hypotenuse, longer leg to hypotenuse, shorter leg to longer leg. And it really isn't, because both legs are the same. So leg to hypotenuse would be 1 to radical 2, and leg to leg is going to be 1 to 1, because there is no shorter and longer. It's just the leg and the hypotenuse. So the ratio that represents leg to hypotenuse is going to be 1 to radical 2. Written as a fraction, that's 1 over radical 2. We don't like to leave it like that, though. We want to rationalize. So we multiply top and bottom by radical 2. So this ratio is really radical 2 over 2 when you get done. So the 45, 45, 90, it's an isosceles triangle. So both sides are the same, and this is 45 degrees. If I wanted to generalize, I could say this is 1x, and this is 1x, and then the hypotenuse is x radical 2. So the ratio of leg to hypotenuse is 1 to radical 2. Or it's x to x radical 2, if you want to solve for this. So let's solve using those ratios. If I have a hypotenuse length of 20, I want to find the lengths of the legs. So remember, our standard form is x, x, x radical 2, and now what I have is 20. So 20 is going to be equal to x radical 2, which means I want to solve for x. 20 is equal to x radical 2 divide by radical 2. I get 20 over radical 2 is equal to x. We don't like to leave it like that, though. We want to rationalize. So if I take the 20 over radical 2 and I multiply by radical 2 over radical 2, I'm going to get 20 radical 2 over 2. Simplify that down because the 20 divides, the 2 divides into the 20, and my two side lengths are 10 radical 2, 10 radical 2. So that takes a little bit of work to go from the hypotenuse to the side lengths. But let's go the other way. Let's say a triangle has a leg length of 20, and I want to find the other leg in the hypotenuse. Well, this is the easy one, because if one leg is 20, then automatically the other leg's going to be 20, and the hypotenuse is going to be 20 radical 2. Well, I got to fix that. So that's how we can use special triangles to solve the sides for sides of similar triangles. We have the 30, 60, 90, and we have the 45 right triangle. We're going to use these later to talk about specific ratios for other angles and some exact values of some what we call trig functions. But for right now, you just need to remember the two triangles and their ratios.